All right, our next speaker before lunchtime will be Dr. Chip-Ing Lee. Chip-Ing runs our energy conversion and combustion sciences portfolio. He's got 30 years of experience in combustion research. That includes early in his career he was at the Naval Research Laboratory. Later on he went to industry with Aerojet, where he was the chief engineer for the Air Force funded or sponsored robust scramjet program. And he's been here with us at AFOSR for the last 2.5, 3 years. This is his second opportunity to come up and tell us about what he's doing in this program in Spring Review. He's also an associate fellow with the IAA, and he's the chair of one of the propulsion technical committees at AIAA, so he's very active in the society as well. So, Chip-Ing.
Okay, thank you. Let's see, how do I... Guess I put it here. Where does this thing go? Where's the, oh, right here. Thank you, John, for the nice introduction. And good morning. I run, as John mentioned, I run the energy conversion and the combustion science portfolio. I'm Chip-Ing Lee, and we're going to describe the portfolio this morning. And the portfolio attributes really is stated there. We strive for fundamental, relevant, and game-changing. So what do? We deal with the energy conversion process to satisfy Air Force propulsion and other system needs, including fighters, transport, and missiles, UAVs, and also including the ever-increasing the subsystem energy needs. And for example, the guidance and the navigation system, they depend more and more energy. They're all from the same energy source. At this time, probably in the foreseeable future, most of them are from combustion. And there's no way around it. And And then, so there's a large part of a majority part of a portfolio deal with combustion. Basically, there are two major challenges. One is the turbulence, the fluid dynamics, the energy release from the chemical reaction. Then the other one is the underlying chemical reaction process. So that's what the portfolio all about. And what's the underlying principle? Actually, we have two. We should have one more. The principle is fundamental and relevant. Also, we strive for game-changing ideas. Why do we say fundamental and relevant? Because the combustion field, combustion area, the landscape is very extensive. And the phenomenon, the nature of a phenomenon changes from the conditions and from the system. So we are doing fundamental research, try to understand the key understandings in the relevant phenomenon. I will further explain to that. And in this portfolio, we have unique opportunity to address, to deal with some time-honored fundamental scientific challenges, i.e. the turbulence combustion and combustion chemistry. Turbulence combustion itself, turbulence itself is challenging enough, but which actually I would consider is, to me, I have this story planned for earlier reviews. I hope someone to ask the question. I never get asked, so I'm going to give away the story anyway. So when I was a graduate student and I studied, I'm trained as a quintessential combustion scientist early on. And I studied with a fellow, fairly well-known, called Saul Penner, who trained a whole slew of the top combustion experts. So we have this room, we have this debate going on, on the turbulence model, on the chemistry, how to reduce it. So at that time, I look at it, I think this is no way to do the business. I don't see a way out. So I made a pledge to myself. I'm not going to touch this two fields in my lifetime. So I stayed with the extreme end of the combustion process, which those processes probably have a converged effect. Then once I started going to the industry leading the large engine development method and coming here and find out those are really the confluences of the key problems in the energy conversion process in our engines. I have no way around it. If I'm not dealing with this, I'm not honest to myself, to the portfolio. So basically we have to deal with it. So that's the two areas. Really is the confluence of long-standing fundamental challenges, which is crucial to Air Force needs. I explain you why. Then there's a third area which we explore new energy conversion concept, more clever concept, how we do it differently. So in this portfolio, we have unique opportunity to address those long-standing scientific challenges, to make headways, to have significant impact on our engines, and also we have opportunity and to play some fun things. So currently, these two pieces are in place, and the combustion chemistry will take longer time, and turbulence flame, we are capturing a lot of things we can. And so with those two in place, we will in the future focus on this little bit exploratory, game-changing things. I will probably at the end of that and tell you, where in this area we like to go. So the other thing, if you're dealing with a combustion, turbulence combustion and combustion chemistry, the problems are quintessentially and multidisciplinary. So we collaborate extensively with other portfolios. Mike Berman's portfolio, as Mike mentioned. Some of the things we developed was used by other portfolio like Dr. Birkin's portfolio. And then we also collaborate with different agencies in different areas. That's essential for the success of the portfolio. The first area I'm going to show is the turbulence flame. Since this portfolio is a little bit different, we have those time-ordered challenges. So we have those emphasized. So the flavor of this presentation is probably a little bit different. And we will illustrate, use one example, and to tell you a story how we handle this one, and with some background information. In the combustion chemistry, I have two very good examples how we approach the problem. And those stories will be a little bit more extensive, just one chart. Will be a couple of chart stories, and I will go through that and explain that's needed. So in the turbulence combustion area, we are focusing on the fundamental flame properties in the Air Force relevant regime. And then those things, the understanding from those properties will give us the foundation for build first principle and experiment data-based models. So why do we study the turbulence combustion, turbulence flame? It is this is actually the impact. It's the most important determining factor of the operability and efficiency of engine. I explain why. It is least understood area in the fundamental combustion research. Actually, the turbulence is one of the remaining biggest problem in physics. And then it is confluence, is particularly and fortunate. It is confluence of this grand old scientific challenge and have immediate and long-term Air Force interest. Why? If you look at a jet engine, and the jet engine if you look at jet engine, the combustion process have two key components. One, we call the recirculating flame holder, which basically maintain the pilot, like a pilot in a stove. It's basically keep the engine flame going. And then the flame propagates through that. So the operability, the flammability limit of this and the flame holder determines operability. When the engine goes off, if we have a sudden extinction of the engine, and then you will lose the trust. And how fast this burns, determined by turbulent flame property, really give us the efficiency, because the quicker you burn and the more efficient the engine is, and you can build a shorter engine, lighter engine. So those are the quantifiable and matrix we can apply. And then the screw injet is exactly similar, it's exactly the same thing. We have flame holding area, and then we have a flame propagation. So those are the two key things. That's why, and we need to study this. This is why, this actually is basically, as the title says, where and how well engine works. So what do we do in the portfolio? What we do is we focus on understand the flame property using the modern diagnostic techniques has been supported in this portfolio in the last 30 years. I'm really grateful my predecessor, Julian, put a significant persistent investment in this area that allow us to be able to look into and what the flame look like, what detailed flame structure look like. Before that was not possible. Then once we understand, we have the experiment data for the key flame structures, then we can build the modeling foundations. Here, what we want to tell is why do we stress relevance here? And why can we study all the flames? That goes from the early question. Because the landscape is quite extensive, and the phenomenon you encountered is quite different in the combustion field, in a different type of flame. So we have to focus on the ones in our interest. This is a typical we call the regime map. There are 3 axes. And this is one of the contribution of our key contribution of our PIs. This regime map is like Cedric's map in Harry Potter, so tell you where things are. And this axis basically is the chemical reaction scale, how fast chemical reaction goes, and relative to the flow time scale. This one is Reynolds number, like it's basically the intensity of turbulence. This axis is pretty new, and in the past people haven't focused on it. And this Mach number basically is how compressed the air is. And this is one of the contributions of the PI in the recent time we look at in this axis, because this is relevant. All the Air Force engines are in the compressible regime, Mach number ranging probably from 0.1 or 0.2 to all the way to supersonic or hypersonic. So this is the regime map. Next one I want to show is, and in this regime map, if you have a laminar flow, a laminar flame like what you have in state, is this very nice looking and curved flame. And if you become a little bit more turbulent, then you see the flame ball, the wrinkled flame ball. If you go to further turbulent, and in the more compressible condition, you get this little flame burning and the flamelets, the broken flame. You know what tell us is, this is a burn much, much faster than the other. Then, what's the engine flame? This is the high-speed movie taken by Dr. Mel Rockmore at AFOSR in high-speed video, also probably developed by under my support of my predecessor. Is this kind of flame is somewhere here. And the first, we always thought, we ride on the plane every day. We understand the flame. But once I look at that, I got scared for a while. I said, I'm sitting on this thing. If the big flame ball goes too big, engine blows up. If this thing becomes too lean, the engine goes off. I'm sitting on this is actually in the current generation engine. I'm sitting on the engine with this kind of stochastic unstable structure. You see, I get queasy. Then you know what that tells us is engineeringly, the great engineer in our engine and company, they have to put a lot of margin into it. So the engine has to be heavy, and the things have to be redundant. That's why. So this is why really is key for us to understand that, which was not possible before we had and those diagnostics. So that's why we're doing it, where we're focusing on the relevance of our Air Force. And then this is a cross-section of that regime map. This one I will show you. If you move around this regime map, the flame and structures are very different. They can burn very fast, very slow. They can have all kinds of behaviors. Those kind of understanding is exactly what we need and to build our predictive models. Let's see if you're with this region, and we have a fairly benign flame curve. And in this axis actually is the, as I said, we call the Kelvin number or something, either Dunkel number, Kelvin number, is the reaction time scale. This axis basically is the equivalent to the Reynolds number, to the turbulence intensity. Then if you go to further up in the turbulence, you see the flame become much more wrinkled, and you see the overall burning speed become much more fluctuating. And if you go to this side, the reaction gets faster, the flame is broken. The flame is broken, and many, many small flamelets that burn very fast. Then if you move up, and you see even more distributed flame. And the other interesting thing is the flame itself, in this case, you see the big fluctuation of the thing. One of those fluctuations sometimes become big enough to cause detonation, and which is another phenomenon which can be disastrous in the engine, or on the flip side, and which can be beneficial if we have a post-detonation engine. And so what does it tell us? The flame structure really is a strong function of the turbulence conditions. That's what we need to understand. That's what we need to find out in those engines, or in the future engines, what's it going to look like to build our models. The other interesting thing, if we go to further, the combustion itself will generate more turbulence. We do this numerical experiment. As we keep going on, the turbulence around the flame will go up. So that basically tells us really we have begin and to understand the turbulence structure in our relevant regimes. And then what do we do? What do we see in the physical experiment? We'll see the very similar thing. And this is the newest and PLIF. You see the flame when the turbulence level from very benign to more and more intense. And what that tells us? Basically, we have more and more wrinkled flame surfaces, so the stuff burns faster and faster. And then those detailed measurement gives us how the flame is stretched, is doubled, is rotated. And this is, again, same thing. And we have those strong turbulence and very high Reynolds number conditions. And this experiment tells us the same thing. If you change the turbulence condition, and the burning speed gets higher and higher. So that next chart is the same thing. This is the turbulence level. This is the total burning rate. You see as turbulence goes by, the burning speed got even higher. This is very interesting because in the community, people have been sort of pre-assumed based on some experiment, the speed will flatten out, which that means there's a limit for how fast you can burn stuff. But the more and more experiment tells us in many regimes, the flame speed goes right up. So there are two very important implications we can draw in this one. One is we need to find those regions to build engine there can burn more efficiently. Also, we need to be careful, and so they don't burn super fast, become detonation. So those all have very immediate impact on engine design, and which actually I draw this thing from early my experience as a chief engineer. And when we designed the scramjet engine, people ask how short the engine is. You know, how fast you burn this stuff? I said, I don't know. I said, oh, well, you're supposed to know that. I don't know, we don't have data. And now we have those data. So that's very, very encouraging and beneficial. So all the things will not be possible and if we don't have diagnostics. So this portfolio benefit tremendously from previous investment. So we are keep making the investment for the future in anticipate where the future engine goes. And multi-phase and droplets environment. This is a great work done in joint collaboration between AFOSR and funded by this portfolio with DOE advanced photon source at Argonne National Lab. And basically what it tells us is use the X-ray generated by those advanced photon sources to shoot through the droplets, measure the droplets and distribution, which is for the future engine injectors. And so, again, to further illustrate, those are the long-time persistent investment. And this is another example about the special type of absorption measurement, spectroscopy measurement, called the tunable diode laser absorption spectroscopy. Basically, it's a laser shooting through the engine, and then you can tune the frequency to measure different species and the temperature. And that's pioneered by Stanford University. And Professor Hansen at that time is Dr. Hansen, who was a postdoctoral research fellow. And then from 1970s all the way to 2010, the things evolved from the university laboratory experiment all the way to the flight test, high fire test. In the meantime, when become very famous, Professor Hansen, now the member of NAE. So that's really the showcase of the persistent investment. I'm sitting here, take the credit, really belongs to Julian Tishkov and my predecessors. And also, we are having timely transition about the model foundation and the improved model based on our understanding in the flame and the physics through different STTR rules and to pass them to the laboratories, to the industry. Actually, we have a series of the STTRs ranging from radiation model to turbulence model to supercritical area. Some of them are being awarded, some of them in the process. So those are the turbulence flame where we are. So after this 2.5 years, and actually I got much more than I expected. I thought it was very tough, right? This area I swear not going to touch. In my lifetime, I touched it actually based on the community, due to the community support, and also my predecessors' good foundation. Really, we have a great progress. We begin to understand the flame structures, and they translate into the modeling foundations, and then the work actually being continuously transferred as through STTR the things to the applied community. The next one is another interesting challenge, is combustion chemistry. This is an underlying chemistry process and for the combustion. And this is also where Dr. Berman and I have a greatest collaboration. It's very enjoyable. What it is, if you think about the combustion process, is basically you have those molecular systems. They're moving from low energy state, higher energy state to lower energy state. In the meantime, bonds breaking and the energy came out, become heat. Then the heat was used to heat the gas and pushing the stuff around. That's the propulsion. If you want electricity, you may have some chemoelectric process, or use this little heat to push a little generator or something. And they call it APUs in the airplane to give you electricity. So this is really from the mind where the energy is from. You know, Dr. Berman created all the molecules and hopefully get the energy stored. I need to get it out and to push the stuff and to generate the electricity. Then if you think about this, this is like this. I rather like this one, like the waterfall. Water goes from high stream to low stream, and high place to low stream when we can harvest the potential energy. But the important thing is not only that. Is, you see, the water doesn't go anywhere. Water stays in the key pathways. This is very important to the game-changing effort. I'm basically the seat here. And you see, in the existing combustion chemistry model, they have this combinatorial approach, try to include every reaction. But our contention is we don't need to include every reaction. We need to include only important pathways. The water doesn't go to the treetops. Rarely the water, maybe some splashes go to the top of the rocks. But mainly water stays in the gutters and they flow down to the pond. So what we want to do here is follow the nature, follow the pathways, and we remove the empiricism, ad hoc empiricism, replace that with more and more ever-increasing first principle foundations. And further to illustrate the point, some people take a great pride of the things, but this thing really give me some headache. You see, in the past, how many years? Maybe 30 years? The number of species and in our combustion chemistry model keep increasing to about 10 to the 5. Number of reactions become 10 to the 6. So people think, oh, we need a grand challenge program. We need a bigger computer power to solve. This is a great justification to those resources. But when we think about it, it's really the best we can do is really physically sound. There are a couple of remarks. Number one, the Uranus model, the chemical reaction model we are based on, are model. They have their limitations. They are not like gene bits, which is, if you're religious, it's God-given. Otherwise, you will say it's being through the evolutionary process. This is a model. It is not exactly gene bits. The second one, there are too many parameters, too few data to anchor those parameters. Actually, in those kind of models, there are only maybe 5% or less the reactions are actually based on actual measurement of ab initio calculations. Number three, it's just too big. If you go to any engine companies, 10,000 reactions, 100,000 reactions, that's beyond current capability of CFDs. So what we need to do is we need to find a game-changing approach, much more fundamental and much more practical. This is another interesting thing. People think fundamental and practical are diametrically opposite to each other. But if you understand science, they can help each other. You don't have to have this big model. You can be more fundamental and resolve the smaller model. And this is what we want to do. The objective of this new approach is have a physical-based method of limited reaction steps with acceptable uncertainties and usable for our simulation tools. So this is what we want to do. And so basically, what do we do? Again, follow the pathways. And so this is a potential energy landscape. It's like our waterfalls. We try to find out what's the most important pathways. So how to do with that? We need good quantum mechanism, fast, to express those landscapes. Mike Berman helped a lot. We need to further develop. Also, this actually approach gained the DoD-wide traction. Basically, ARO and myself, we are working together, and we probably will be working on that for the next 10 years or so, because it's very fundamentally different. But we have some short-term benefit too. And then we need to search those landscapes to find out the pathways. Then we need some experiment approaches to tell us how reaction proceed. And not just a static measurement to see the species concentration. We need basically reaction trajectories at very short-term basis. Then we need more ab initio and method to process the experiment data. So this is what we want to do. And first, the experiment, we are also benefiting and the new development of the combustion diagnostic, other diagnostic. We are in this time scale which we can look how reaction proceed. This is a very nice chart from Jim Ford and from AFOSR. He laid out at different time scale what happens. But that's where we're looking at. We have already had a femtosecond laser. We are working on autosecond things, allow us to see those chemical reaction process. Actually, I'm rather fortunate because of good PIs, and they really performed far better than expected. This is the one Dr. Berman mentioned, and used to be in his portfolio. Now we have a new task for him to find out reaction pathways. And he has some very encouraging preliminary results. Basically, this is the pyrolysis, i.e. the thermal decomposition of a propane. They laid out the pathways, some pathways actually which has not been documented, and he is working on to find out, to determine what pathway is more important, and find out, build those algorithms to determine that. Next one is a different method, and basically it's molecular dynamics of some flavor. They also track down the pathways. They find out the new pathways, and which is in the green, and also they are working on how to basically determine which one is more important. So we are moving ahead. Consider this project, this whole area, multiple projects, is about a year old. And so we are really doing quite well. And then, this one is I'm particularly fond of. You see, we have those very complex turbulence flames. We have those ab initio approach we want to pursue, probably will take a while. But the AFOSR, everybody, they need the intermediate reaction models. We cannot wait that. And the other one was 100,000 steps. It's too much. And have all the holes in it. So what do we do? So what actually we do is we take advantage of nature. The people talk about this what called turbulence-chemistry interaction. If you go in the community, that's a buzzword. But that was buzzword is mostly a lot of people paying the lip service. No, it's not really entirely how to deal with. They try to show that it's important. Now we know it's important. We need to find out the pathway to deal with. Here we have a way, and because of our really good PIs who work on that. What happened is, if you look at the flame structure, that gives you a hint and how to do that. That actually let you find simplicity in the complexity. That's the things I really like, And if you look at the nature, there are seemingly intractable things, but you see them, oh, there are some things we can find out. What we do is in those turbulence flame, the flame gets thicker. You have a fairly thickened, and we call it pyrolysis region. The fuel breaks down in those regions in a similar pattern. That's being shown on the turbulence flame side, also on the chemistry reaction side. They all find out is similar products coming out. So that gives us very interesting approach. What we do is we can build experimental-based pyrolysis model for the fuel decomposition. Then we can relate, when the fuel decomposes relatively small molecules like ethylene, methane, or those things, we can use the lower left corner from your perspective of this map. Those are actually the most validated and the best, and compared to experiment model, best anchored model. So we built this. This one is actually being and the transition already to RQH for the high-speed side. We're working on the turbine engine. You see, the thing is, the interesting, the philosophical under that is, the more fundamental combustion chemistry area is, I would call ab initio-based experiment constraint. Now, because that will take a while, so what we do in the near term is we flip it. It's experimental-based ab initio constraint. So get us a near term until we build this framework. So that's where I go. This is really, I consider, I have to say I'm really grateful to the good foundation set by Julian for all my good PIs. This is not only game-changing, also immediately useful. And also it is fun, it is interesting. It's based on the nature, based on the physics. So, and that's why I said the preliminary model is for the JP8 and for the hypersonic fuels. For the JP8 still under development, will be sent to the lab probably later this year. For the RP2H, which is a replacement of JP7, it's already been sent to the lab. So lab will run it compared to their test results to see what's going on, send feedback to our PIs. So that's where we are. That's basically 3 examples of the program. One, turbulence flame, leads to the more shorter compact engine, better fast burning engine. The other is a fundamental game-changing combustion chemistry. The other 2 is intermediate process to address needs based on the science, not ad hoc empiricism. And then where do we go from here? We anticipate the future. The Air Force engines, not Air Force engines, all the jet engines, next generation, is going to be at high pressure environment, about 50 bar. In that environment, the things change. The two-phase change is becoming supercritical. We need to deal with that. The other one is we become more exploratory on the multi-fractioning fuel and the energy system. For example, fuel can also, in addition to its function of the provide energies, also become a cooling agent or other things, maybe lubricant. Another area is the energy source for the UAV and small vehicles, also for the subsystems. And like the information system, they all need energy. We'll have to take a look at that. What's the nature of those things? For example, we need energy to process information for the onboard computers. What's the energy cost? The thermodynamic principle of it. So that's where we are. So closing statement is, we are pursuing fundamental, relevant, and game-changing. And we captured the opportunity, unique opportunity to address those long-standing challenges. And we started to, with those things are in place, we started exploring the new things. And then after 2 years, portfolio is really taking a good shape. Support projects are showing the results, showing the breakthroughs. Have you seen it? And we'll keep exploring. The more to come. Thank you. Question?
Yes, question.
I was just curious about the role that plasma-assisted combustion might play in your effort to decrease the size and weight of the engines, and also maybe in the chemistry investigations.
Yes, the plasma-assisted combustion was an integral part of it. It belongs to the third element. We had a Murray, and the Murray's top Murray since last year. The Murray's goal is to produce a first cut of a plasma combustion joint mechanism. And in the light of this development, probably they will have to absorb some new thinking, and instead of start with a big thing, they look at what's the key pathway. The interesting with the plasma, and it is the elevated electronics, the state, that makes things become quite difficult. So how will we go from there? Well, I'm still working on it, but it is an integral part of it. On the applied side, it does help us to for extend the operability limit. But certainly there's a trade-off. In the real engine, you need to carry that electric source to supply the power and their discharge efficiency, all those things. So where things go, and the part of them we already transit to the RQH for them to look at, and the part of them we're still working on. But it's a longer time challenge. Anyone? Oh.
This is maybe not a question for you, but maybe for John as such, but in your last, second last, third last slide, you had a UAV, and I noticed a propeller. And do we do aerodynamics on propellers? And,
Thank you.
Sure, thanks. I'll need the microphone. So
okay.
The question is, do we do aerodynamics and propellers? Propellers specifically, no. Do we do relevant work that could be applicable to propellers? Absolutely. The things you see in Doug Smith's portfolio for flow control under various dynamic considerations, there's a variety of things we do that would be applicable to that. A lot of the numerical methods we develop would be very relevant. The detached eddy and large eddy simulation types of things have direct play and relevance into propellers. Typically, we don't see a propeller-driven system as being on the forefront of a game-changing Air Force capability. That doesn't mean we're not going to have them involved with things, but propeller technology doesn't seem to be our limiting case, with the one exception of possibility of the brownout issue, which I think the fundamental fluid work and the way vortices are being shed off a rotating lifting surface and the way they interact with particulates on the surface out of Doug's portfolio would, there's some fundamental work being done there. So the answer is no, yes. We're not addressing propellers themselves. There's a lot of work relevant to rotating lifting bodies that we do have a handle on, and I think we're reasonably invested there.
Yeah, to add to John, and from power, okay. For the power supply point of view, right, the propeller need to be pushed, and that's a fairly time-honored engine. And there's one aspect we are looking into to see if there are any fundamental things we can attack. Is the recuperate engine, because engine generate heat, it gets ejected. Can we somehow utilize a part of it? That's called the recuperative engine. The lab is fairly heavy on, not heavy on it, but looking into this. But how we want to help and invest, what's the fundamental issue? You see, we're looking for two things: fundamental, game changing. We're not looking for particular, what they call the design optimization, but we're looking for underlying principle to help all type of design, all type of concept. So that has to be determined to see where we go from there. Any other?
I think everyone's hungry.
Oh, good. Thank you.
John,
Yeah.
1 o'clock return. Start at 1 o'clock.
No, I've heard, hold on one second. For everyone in the room and everyone online paying attention, we're getting a call right now on when we're coming back after lunch. We are going to have an accelerated schedule. I have heard two times. I've heard 1 o'clock and 12:30.
No, we're going to start at 1 o'clock.
Okay. We will resume our broadcast and live presentation here at 1 o'clock. We'll see everyone then. Have a great lunch, and I'll remind everyone that those of us who are at the AFOSR should be in the AFOSR conference room at 11:45.
Okay. Well.